Assalamualaikum. Good morning. Welcome back to my lecture. Today I'm going to record lecture 10, of CHM676 Organometallic Chemistry. And lecture 10 will be on some reactions of organometallic compounds. You have learned from lecture 1 until lecture 9 the properties, the type, and the different ligands that can make organometallic compounds or that can form organometallic compounds with metals. You have learned how to characterize them, you have learned their behavior, and you know that these compounds have very good tendency to become catalysts. That is why they are very popular among researchers, and many reactions have been catalyzed successfully using organometallic compounds. Now I'm going to teach you, or I'm going to go into the reactions of organometallic compounds that make them good catalysts. Why they can behave like that, why they can react like that, and why these properties or these reactions make them potentially very effective catalyst. So organometallic compounds can undergo a variety of reactions which may involve either loss of a ligand or gain of a ligand. It can involve molecular rearrangement, it can involve formation or breaking of bonds to metal and to the ligand themselves. The ligands attached to organometallic compounds can react with themselves, if not with the metal. We will discuss some common reactions of organometallic compounds. Now, the first one that I want to go into is substitution reaction of carbonyl complexes. Yes, we all know. We have seen some substitution reactions in my previous lectures. It is typically presented in L. L is any ligand, M is the metal, and the CO definitely is the carbonyl ligands. And if there is another ligand coming in, which we give a symbol of L prime, this L prime can substitute one of these carbon monoxide ligands, yeah? So you're going to, in the end, after the substitution, obtain L prime, M, CO4. Originally there were 5, now it becomes 4, and the fifth carbon monoxide ligand will be replaced and will be kicked out of the compound. For example, if you have FeCO5 reacting with trimethylphosphine, you may get FeCO4 with 1 trimethylphosphine and 1 CO being released. Now, this reaction represents an important way to introduce new ligands into complexes. This does not involve any change in formal oxidation state of the metal center. Yeah, the oxidation state doesn't change, the coordination number doesn't change. If metal here has coordination number of 6, here it also still has a coordination number of 6. If for example, the charge here is 0, here the oxidation state is still 0. There is no change in either one of the oxidation state or coordination number for a substitution reaction. Now, the kinetic studies of such reaction indicate that substitution reaction may either occur through associative or dissociative mechanism. Associative mechanism is when you have an addition. This is an addition reaction if you have a look. MoCO6 plus L, you get MoCO6 with L attached to it. And if this reaction, or if this first step is a slow step, then we say that that substitution reaction goes through associative mechanism. And this MoCO6L will very, very quickly turn into MoCO5L with a release of CO. That is a fast step. So being a slow step or the rate determining step, an addition reaction makes that reaction an associative, going through associative mechanism. The rate determining step, which is the slow step, involves a bimolecular reaction of MCO6 and L to form an intermediate. So two reactants make one product. Yeah, two reactants make one product. And the intermediate will then lose a CO in a very, very fast reaction. So slow step, the rate determining step is an addition reaction. So you have an associative mechanism. The second type is dissociative mechanism. Now, the reverse or the opposite to associative mechanism, dissociative mechanism has a slow step of an elimination reaction. This is an elimination reaction where you have nickel CO4 becoming nickel CO3 plus CO, and then your nickel CO3 will quickly react with L to make nickel CO3L in a fast step. Now, if the rate determining step is an elimination reaction, so you are having a dissociative mechanism. So that reaction is undergoing a dissociative mechanism of substitution reaction. Now, the rate determining step involves the splitting for the dissociative mechanism, splitting of one reactant to form two products. The product then reacts with substituting ligand in a fast reaction. Yeah. So there are two distinct mechanisms at which substitution may occur: associative mechanism or dissociative mechanism. Now, although most substitution reactions proceed primarily through dissociative mechanism, an associative path is more likely for complexes that have large metal center and highly nucleophilic ligand. Why would a large metal center prefer to undergo an associative mechanism? Yeah, think about it. Because a large metal will be able to physically accommodate this situation where it has 7 ligands around it, even though for a short time only. Yeah, so a large metal center which has no tendency of being crowded, then it can undergo associative mechanism. And on the side of the ligand, any highly nucleophilic ligand will also prefer associative mechanism, because highly nucleophilic ligand is known for its love or its affinity for nucleophile. Nucleophile is your metal. If the L or the oncoming ligand is very, very nucleophilic, no matter what happens, it will still attach itself to the to the electropositive metal. So metal is electropositive. If the ligand is highly nucleophilic, it will attach itself no matter what. If it has to have 7 ligands around it, so be it. Yeah. So associative mechanism is favored by large metals and highly nucleophilic ligand. So the opposite to that, and a dissociative mechanism will be favored by a small metal and a ligand which are not very nucleophilic. Yeah. So for example, here you have nickel. It is quite small. it cannot accommodate more than 4 ligands, so it chooses to throw away one ligand first before it is ready to come to accept the next ligand. Unlike your molybdenum here. Molybdenum here is ready to accept a ligand even though it has a full house, because molybdenum is big. Nickel is small, so it will have to get rid of one ligand first before the next ligand comes in. So a dissociative path, this is associative, a dissociative path will be favored by small metal and ligands that are not very, very nucleophilic. Yep, so that is about substitution. The second reaction that I would like to talk about is called insertion reaction. Now, insertion reaction is when you have a small molecule coming in between your metal and carbon, or in between your metal and hydrogen. We all know that organometallic compounds have metal to carbon ligand. If there is a small molecule inserting itself or coming in between the metal to carbon ligand, so that reaction is called an insertion reaction. Insertion of a small molecule XY, the small molecule would be XY, either X is equal to Y or X is not equal to Y. It is still a small molecule. If XY can put itself in between the two atoms, metal and carbon, that is an insertion reaction. Although some of these reactions are believed to occur by direct single-step insertion, many of such reactions are much more complicated and do not involve a direct insertion step at all. Now, there are two types. Commonly, there are two types of insertion reaction. You have a 1-1 insertion. What does 1-1 insertion reaction mean? On the inserted molecule, remember we are looking into the molecule. On the inserted molecule, the insertion bonds occur only on one atom, as shown below. Now, if you have this situation where you have manganese is bonded to carbon monoxide and then to methyl here, and there is an oncoming CO ligand, if the oncoming CO ligand itself inserts itself between the manganese and the carbon through only one of the atom, which is the carbon, like this situation here, this is called a 1-1 insertion. Carbon is atom number 1, oxygen is atom number 2, and the insertion, the manganese, is attached to atom number 1. The carbon of the methyl is also attached to atom number 1, so this is called a 1-1 insertion. Now, to understand that clearer, you can have a look at the 1-2 insertion. So if you have, for example, this molecule, this small molecule, CF2, there are two, this is a kind of olefin. When the incoming molecule or the inserted molecule, when the insertion bonds occur on two different atoms of that small molecule adjacent to one another, then you call that insertion a 1-2 insertion. So this is a situation where that becomes quite clearly illustrated. You have a cobalt attached to hydrogen, and this oncoming molecule is inserting itself between the cobalt and the hydrogen in this way. Cobalt is attached to carbon 1, whereas hydrogen is attached to carbon 2, and the molecule is nicely inserted between the cobalt and hydrogen. So insertion of this type is called a 1-2 insertion. Yeah, 1-2 insertion as opposed to the 1-1 insertion. Yeah, in this case, the CO is inserted and it's only one atom that is attached to both the metal and the alkyl. Whereas in here, the molecule is inserted, but two atoms are bonded to One is to cobalt and another one is hydrogen. So this is a 1,2 insertion. This is a 1,1 insertion. So we will now look at how small molecules such as carbon monoxide and SO2 insert into a metal to carbon bonds in organometallic compounds. Now, a CO insertion like this one that we see in the first example, which is a 1,1 insertion, a CO insertion is also known as carbonylation because you are putting a carbonyl moiety into that reaction, into that compound. It was found that when carbon monoxide reacts with an organometallic compound like this one, CH3MnCO5, the product becomes CH3CO MnCO5, where the CO has attached itself in between the alkyl and the metal. It seems that the CO has inserted itself between the MnCO3 bond to produce an acyl complex. So CH3CO is an acyl ligand. However, upon further investigation, when scientists use a labeled carbon-13 carbon monoxide, they find that the CO that is inserted between manganese and alkyl is not the labeled carbon-13. The label carbon-13 CO is in the compound, but it is here. It is bonded directly to the manganese. It is not the one that goes in between the two bonded atoms. The conclusion of this study there are many conclusions, one, the inserted CO is one previously coordinated to the metal, not the one that is labeled and added to the complex. Therefore, the CO that becomes the acyl carbonyl is not derived from the external CO, but is one already coordinated to the metal atom. So that is first conclusion. The second conclusion is the incoming CO is added cis to the acyl group as shown in the diagram next. And the third and most important conclusion is that any other Lewis bases, not only CO, can bring about CO insertion as shown in the mechanism below. Therefore, the conversion of alkyl into acyl can be affected by addition of ligands such as PPH3 or any other Lewis bases. For example, ammonia or water maybe. Yeah. How is that? What is the mechanism of carbonylation? Now, looking at what the product was, this is the product. Yep. That is the product. Oh, it's not copying. Yeah. This is your MnCO5Me, and it is obviously dissolved in some kind of solvent. It is suggested that it is the solvent that initiates what's going to happen next. The solvent takes up the position of one of the carbon monoxide, kicking the carbon monoxide here, that one over there, onto this manganese to methyl bond. It is already inserted by the action of the solvent. So when you're substituting ligand, either another CO or a different molecule, when it is added into the reaction, this ligand is simply going to replace the solvent here and take up that position. So the acylation or forming of acyl already happens before L comes in. Yeah. So this is the proposed mechanism through the observation that they find when they put carbon-13 into that reaction. So this L here is carbon-13CO, where it is not found in this as expected. We would expect that carbon-13 would be here, but that's not the case. Carbon-13 is directly bonded to the manganese, and it is a different carbonyl that goes into this bond inserting itself. Yeah. So that is the mechanism of carbonylation reaction. So next, I would like to show you about SO2 insertion of sulfur dioxide onto the metal to carbon bond. Now, unlike CO, SO2 inserts directly into the metal to carbon bond as shown in the reaction below. So if you have this situation, you have metal to carbon attached to R, whether R is H or whatever others. What will happen first is that your SO2 will attach itself onto the carbon, the alpha carbon. Yeah, this is your alpha carbon. And then through um, uh, electron movement, it is then going in between it moves itself from this end into that middle part, like this. And there are two ways. It can either be bonding to the metal through oxygen and sulfur, or the other way. And in the end, what will happen is your SO2 suddenly from this end, from the very, very end outside here, it manages to insert itself between the metal to carbon bond. And if you call sulfur as atom 1, this oxygen at the top as atom 2, and this oxygen at the bottom as atom 3, you will say this insertion is a 1-1 insertion. But there are many other ways in which SO2 can insert itself between metal to carbon bond. You can have a 1-1 insertion like I explained above. You can also have a 1-2 insertion. This is a 1-2 insertion. This is a 2-1 insertion. Yeah, 2-1. Or you can also have something weird happening. You have a 1-3 insertion. Yeah, 1-2-3 insertion, because this is atom number 1, this is atom number 2, and this is atom number 3. You have a 1-2-3 insertion happening. So in the three cases above, this case, that case, and this case here, the coordination number of metal does not change. If you look at this limited view, you will see that metal starts with having coordination number of 1. Here it still has coordination number of 1. Similarly with this one, coordination number of 1. Yeah, with the metal here also 1. But if the SO2 bonds in 1-2-3 manner, then the metal center will have coordination number of 2. Yeah, added. Yeah. The coordination number of metal center increases in the SO2 insertion reaction in here, but it does not involve any change in the formal oxidation state of the metal center. Yeah. Therefore, it is classified as a simple addition reaction. Yeah. This insertion is just simply adding SO2 or simply adding CO into the reaction. But when the increase in coordination number is accompanied by an increase in the oxidation number of the metal center, the reaction is classified as oxidative addition reaction. Now you have oxidation happening, addition happening. So if you have an increase in coordination number, you also have an increase in oxidation number of your metal center, then the reaction is classified as oxidative addition reaction, which leads us to that reaction next. So this is the third reaction that I'm going to explain to you about oxidative, which is the oxidative addition reaction. Now, another common reaction for organometals is oxidative addition, in which a low-valent transition metal complex reacts with a molecule XY to produce another complex with both an increase in the oxidation number and coordination number, as shown below here in this picture. Now, usually, both the oxidation number and coordination number of the central metal are increased by 2. For this to occur, there are 4 things that must be obeyed. For oxidative addition to occur, 4 conditions must be observed. The first condition is the metal center must be D2 or greater. Why does it have to be D2 or greater? Why do you think? Because if there is no electron in the metal, it's not going to be able to undergo oxidation, isn't it? Because to undergo oxidation, through the name is oxidative, to undergo oxidation, the metal must be able to lose electrons. If there are no electrons to start with, well, there is nothing for it to lose. So oxidative will not happen. So the metal center must be D2 or greater. That's the first condition. The second condition, the metal center must be coordinatively unsaturated, i.e., it can still accommodate addition of 2 more ligands around it. If the metal already has 6 ligands around it, which is the maximum, the common maximum number of ligands attached, then it will not be able to undergo addition reaction because it is already physically full. Yeah, adding 2 more ligands will not be able to happen if you already have 6 ligands attached to that metal. So if then oxidative addition were to happen, then your metal must be having less than 6 ligands already attached to itself. It must be coordinatively unsaturated. And number 3, the metal center must have empty orbitals. Empty orbitals that are appropriate, yeah, to accommodate the donated lone pair of electrons. If you can recall, each one of each ligand that would like to attach itself to the metal will donate a pair of electrons. Now, if this pair of electrons cannot be accommodated by the metal because there are no empty orbitals, then this bonding will not happen. And for metal to be able to accommodate the lone pair of electrons donated by the ligand, it must have empty orbitals, and that can only be observed in transition metals. You cannot have this happening for representative metals because representative metals do not contain d orbitals that would accept the lone pair of electrons. And number 4, the donated the compound must have less than 18 electron, obviously, because if the compound is already 18 electron or obeying the 18 electron rule, it cannot add more electrons. It will be because it will violate the stability rule. The stability rule is the 18 electron. If it has already 18 electrons, no oxidative addition will occur. But if it has less than 18 electrons, then the compound has a tendency to undergo oxidative addition, or sometimes given the symbol of OA, yeah, oxidative addition. So this is the example. If you look at this compound, iridium, chloro, PPH3, 2 twice, and CO, this is the Vasquez compound. Well, you can try to name this compound. So it's carbonyl, chloro, bis, trimethylphosphine, iridium 1. How do I know this is iridium 1? How do I know this is iridium 1? Because this ligand is 0 charge, this ligand is 0 charge, this ligand is 0 charge, that ligand is -1 charge, and the whole of this compound doesn't have any charge. So your iridium must be +1 to counter the -1 of your chloro. So when Vasca's compound is reacted with a chlorine molecule, this is your small molecule, looking at your iridium, if you count the electrons, it has only 16 electrons. You can count 2, 4, 6, 8, and 8. Iridium 1 is 8, so you have 16 electrons. So by having 4 coordinate, the B is fulfilled. By having D8, A is fulfilled. By having 16 electron, D is fulfilled. And by having iridium, C is fulfilled. So all the 4 conditions are fulfilled by this Vasca's compound. So when chloride is added to it, it will easily undergo oxidative addition to add 1 chloro at the top and 1 chloro at the bottom. So this is an example, a simple example of oxidative addition. And if you count the electrons, you're going to find that it becomes 18 electrons with the addition of this chloro. And the oxidation state of iridium goes up from iridium 1 to become iridium 3. That is why it is called oxidative. The coordination number goes up from 4 to 6. That's why it's called addition. So oxidative addition reaction. Yep. So that is an example of oxidative addition that is proven through the electron counts and coordination number count. When chloro is added, 2-chloro is added onto this Vasca's compound, there is a decrease in the electron density of the metal as the reaction proceeds, obviously because chloro is electron withdrawing group. So this iridium will be electron poor compared to that iridium over there. Yeah, this iridium electron poor, so it will not be able to donate to do pi back donation to CO very effectively as this one here. So there'll be less electron pi back bonding in the product, and less pi back bonding will cause the strength of the CO bond to increase. And it's reflected through the infrared peak. In the reactant, you can see that nu CO is less than the product, indicating that the CO bond in the reactant is weaker than in the product, and this reduction in the CO bond strength is because of the decrease of the pi back bonding. Decrease of the pi back bonding because the iridium in the product has less electrons through the pulling or withdrawing effect of your chlorine. Yeah. It lowers the pi back bonding from metal to CO, effectively increases the bond order, hence the bond strength of the CO, increases the CO bond strength, increase in CO bond strength is reflected in the stretching frequency that goes from low to high. Yeah. And you can also have this thing happening here. What do we have here? You have metal attached to n number of L, and you have XY, which is a small molecule, and if M fulfills all the 4 criteria above, Y and X will be added to the metal. Yeah, in this way. Similarly, like that also, it can happen. For bimolecular example, if you have MnCO5 twice, this you have seen the dimer, yeah, in my previous lectures. in a few exercises that we've gone through before, you see that MnCO5 twice is an 18 electron species, but bromine molecule can still add to it because it will break this bond and make two separate monomer of, or two separate molecule of MnCO5Br. Yeah. So that is also an example of oxidative addition. And I'm going to then, once you understand oxidative addition, I'm going to go into the opposite reaction to oxidative addition, which is reductive elimination, RE. It is exactly opposite. Yeah. The opposite reaction to oxidative addition is reductive elimination, where the opposite happens. Both the oxidation number, coordination number of the metal will decrease. Yeah, if you remember, in OA you have these two becoming higher, but for RE, these two items, the oxidation number, coordination number, will decrease with elimination of ligand as simple molecule. If before in OA you have addition of simple molecule, for RE you have elimination of simple molecule. Now these are the two most important criteria of reactions of organometallic compounds that make them good catalysts, as you will see in my next lecture. So for example, if you have tantalum bonded to 3 hydride ligand and 2 cyclopentadienyl ligand, it can undergo reductive elimination where the hydrogen, the hydride here, will be released as H2 and leaving behind only one hydride bonded to tantalum. So if you look at the oxidation number in the left-hand side, tantalum is 5 oxidation number, and coordination number is also 5. Yeah, 1, 2, 3, 4, and 5. But after reductive elimination, you're going to see that your tantalum has become tantalum 3. It has reduced, and also the number of ligands attached to it also has reduced. So it only have 1, 2, and 3. It only has 3 ligands attached to it. So forward reaction is RE, but if you look properly, the backwards or the reverse reaction is OA. TAH cyclopentadienyl added with a small molecule hydrogen will make this, and going to the left is OA, then going to the right is RE. So that is an illustration of how reductive elimination is exactly opposite to oxidative addition. So I'm going to stop my lecture 10 here. So as a quick recap, you have learned about substitution reaction. Yeah, you have learned about insertion reaction. You have learned about oxidative addition reaction, and you have also learned about reductive elimination reaction. And in my next lecture, which is going to be my last for this course, you're going to see how these reactions make organometallic compounds good catalysts. So thank you very much for listening. I hope you understand my lecture number 10, and then we will see you I will see you in my lecture 11. Thank you very much. Assalamualaikum.